When you look at a glass of tap water sitting on a table, or even just a pinch of white salt resting in your hand, you tend to see stillness.
Right, you just see objects at rest.
Yeah, exactly. You see the inanimate world just kind of existing completely undisturbed.
We're biologically wired to perceive those everyday objects as being totally peaceful. We see inert materials just sitting there, completely harmless and structurally stable.
But if you actually zoom in, like if you could somehow put on a pair of molecular glasses and see the universe at the atomic level, that peaceful kitchen isn't peaceful at all.
Oh, not even a little bit. It is a landscape of constant, relentless warfare.
It's a chaotic battlefield.
Truly. I mean, trillions of molecules are colliding every microsecond. They're actively tearing each other apart, stealing electrons, shattering bonds.
Just aggressively neutralizing threats before you can even blink.
Exactly. What looks like a calm glass of water is actually this microscopic ocean of restless, charged particles just desperately looking for a partner to latch onto.
Well, welcome to the Deep Dive. Today, we are taking a really fascinating stack of dense scientific research, historical data, and chemical analysis all about acids, bases, and salts.
And we're going to distill it all into a journey for you.
Right. So if you're prepping for a project or trying to catch up on some fundamental science, or, you're just insanely curious about the hidden chemical battles happening right inside your stomach.
Or in your morning coffee.
Yeah. Or even in the clouds of other planets. You are in the exact right place. We want to get you those aha moments without drowning you in an ocean of overwhelming textbook jargon.
And I can guarantee by the end of this deep dive, you are going to view your toothpaste, your baking ingredients, and even the dirt in your backyard in a completely new light.
I love that. So where do we even begin with this invisible war?
Well, the fascinating thing is we have to start with our own bodies, the fundamental experiences we have with food.
Like tasting things.
Exactly. The sharp sourness of a lemon or the harsh bitterness of a dark vegetable. Those are actually our bodies functioning as highly sensitive chemical detectors.
Oh, wow. So our taste buds are literally translating this invisible chemistry into sensory experiences our brains can actually understand.
Right. Long before humans had complex lab equipment with, digital readouts, we tested these molecular structures just by eating them.
Okay, let's unpack this. Because that is such a cool, almost sci-fi way to think about taste. We use terms like acid and base all the time.
We do. And as a general rule, acids taste sour. Think of biting into a raw lime.
Makes my jaw tingle just thinking about it. And bases taste bitter.
Yeah, like if you've ever accidentally gotten a bit of soap in your mouth while taking a shower, that bitter, awful taste is a base.
But obviously, as a survival mechanism, we can't just go around tasting every mysterious bubbling liquid we find in nature.
No, absolutely not. That is a very quick way to end up in the emergency room. Or worse.
Right. The human tongue is a great sensor, but it's super vulnerable to corrosive damage.
Which is exactly why, historically and scientifically, we needed indicators. We needed a way to detect the invisible chemical nature of a substance from the outside.
Without having to risk chemical burns to our actual mouths.
Precisely. And the beautiful thing is, nature has actually provided us with some incredibly elegant, ready-made tools to do exactly this.
And the most famous one, which you probably vaguely remember from middle school science, is litmus.
Litmus paper, yes, the little strips.
Red turns blue, blue turns red. It honestly feels like magic when you're a kid.
It really does. But what's really interesting is where litmus actually comes from. It isn't just some artificial compound cooked up from scratch in a sterile lab.
Right, I was reading this in the sources. Litmus solution is actually a purple dye extracted directly from a living organism.
Yes, specifically from lichen, which belongs to a division of plants called Thallophyta.
Wait, lichen? Like the crusty, mossy-looking stuff you see growing on rocks and tree trunks.
Exactly that stuff. Lichen is this fascinating organism because it's actually a symbiotic relationship between an algae and a fungus living as one.
That's wild. So how do they turn that into an indicator?
Well, for centuries, chemists have been taking certain types of this lichen, crushing it up, and extracting a complex mixture of dyes from it.
And when you put that purple lichen juice in pure water, like totally neutral water, it just stays purple. Right.
Perfectly calm, neutral purple. But the moment it encounters an acidic environment, the molecules in the dye physically shift their structure.
They literally change shape.
Yeah, and that changes how they absorb light. Suddenly, the liquid turns bright red, and if it encounters a basic environment, it shifts the other way and turns a deep blue.
So it's essentially a botanical mood ring. The plant juice is literally reflecting the chemical mood of the water it's sitting in.
That is a perfect way to visualize it. And litmus isn't the only natural mood ring out there. The natural world is totally full of them.
Like red cabbage leaves, right?
Yes. Red cabbage and the colored petals of flowers like hydrangea, petunia, geranium, they all contain organic pigments called anthocyanins.
And those pigments change their molecular shape based on the chemistry of their environment.
Exactly. A gardener can actually change the color of their hydrangea flowers from pink to blue simply by altering the chemistry of the soil they plant them in.
That is just crazy. But there's another natural indicator in our research that I think almost everyone listening has accidentally experienced at least once.
Let me guess. The dreaded curry stain.
Yes, the turmeric reaction. Picture this. You're eating a delicious, vibrant yellow curry.
A dangerous game if you're wearing white.
Exactly. A single drop falls off your fork and lands right on your crisp white shirt. Bright yellow stain.
And that yellow color comes from turmeric, specifically a compound called curcumin.
Right. But the real magic, or I guess the tragedy for your laundry, happens when you take that shirt to the sink.
You grab a bar of soap,
Oh.
you start scrubbing the yellow spot.
And suddenly, right before your eyes, that yellow stain mutates into this deep, angry, reddish-brown color.
And the reason for that rapid color shift is entirely chemical. Soap, by its very nature, is a base. It's alkaline.
And the curcumin in the turmeric is a natural indicator.
Yes. So in a neutral environment, it reflects yellow light. But when you introduce the strong base of the soap, the hydroxide ions in the soap actually attack the curcumin molecule.
They literally pluck off a hydrogen atom.
They do. And that slightly alters the geometry of the molecule. So instead of reflecting yellow light, this new shape absorbs different wavelengths and reflects reddish-brown light.
It just alters the geometry of the pigment. That's so cool. And what's amazing is when you rinse the shirt under the tap with tons of clean water, it flushes all that soapy residue away.
And the stain turns back to yellow.
You literally watch the chemical reaction reverse itself as the water washes out the base and the pH drops back down.
It's a brilliant, everyday demonstration of indicator chemistry, even if it is super frustrating when you're just trying to do laundry.
For sure. Now, for highly precise lab work, chemists don't usually rely on rubbing curry powder on things, right?
No, generally not. We use engineered synthetic indicators. They have incredibly sharp, distinct color changes. The two most common are methyl orange and phenolphthalein.
Phenolphthalein, that one is particularly striking to watch.
It really is. If you drop it into a beaker of acidic liquid, it is completely colorless. It looks exactly like plain tap water.
But the absolute millisecond you add enough base to tip the environment over into the alkaline side.
It violently shifts from clear to a bright, vibrant, glowing fuchsia pink.
Just instantly. Which brings up a really interesting subcategory of indicators that I frankly had never thought about before today.
The olfactory indicators.
Yes, we've been talking entirely about visual indicators like things changing color, but our sources introduce things that change their smell.
Substances whose odor changes depending on whether they are in an acidic or basic medium. Common examples are vanilla extract, onion, and clove oil.
I found this part so strange. The research mentions taking finely chopped onions, tying them in a plastic bag with some clean cloth strips, and leaving them in the fridge overnight.
And the next day, those cloth strips strongly smell like onion.
Obviously. And if you put a few drops of a dilute acid, like hydrochloric acid, on the cloth, it still smells powerfully like onion.
But if you put a few drops of a dilute base, like sodium hydroxide, the onion smell completely vanishes.
No, wait a minute. How does a strong smell like onion or vanilla just disappear? Does the base act like an air freshener, just kind of masking the scent?
No, it's much more aggressive than that. To understand it, we have to ask, what is an odor?
It's not just a magical invisible cloud.
Right. It is a physical, volatile molecule. Scent molecules evaporate off the onion, float through the air, travel up into your nasal cavity, and dock into highly specific olfactory receptors.
Like a lock and a key.
Exactly like a lock and a key. The physical shape of the onion molecule is the key. The receptor in your nose is the lock.
Okay, so the onion key fits perfectly into the nose lock, and our brain says, aha, onions.
Yes. Now, in an acidic environment, the structure of that scent molecule remains stable. The key keeps its rigid shape.
But a strong base is chemically aggressive in a completely different way.
Very aggressive. The base actually attacks the scent molecule, actively reacting with it and snapping off functional parts of its chemical structure.
It literally breaks the key.
It does. Once that physical structure is altered, the molecule still exists, it still floats into the air, and it still goes up your nose.
But the key no longer fixed the lock.
Exactly. The molecule cannot trigger the receptor. The base essentially blinds your nose to that specific chemical by destroying its identifying geometry.
Wow. It's not masking the scent, it's literally dismantling the scent molecule. That is ruthless.
It is chemistry functioning at the structural level.
Okay, so we know how to detect these invisible acids and bases from the outside, by sight using litmus, or by smell using these olfactory indicators.
But detecting them is passive.
Right. What happens when we let these chemicals off the leash? When acids and bases start actually interacting with other raw materials in the world?
That is where things get explosive, literally. We need to look at their volatile chemical properties, particularly how they clash with solid metals.
So let's examine the acids first. When a strong acid reacts with a metal, there's a fascinating and violent displacement that occurs.
Right, there's a classic laboratory experiment for this. You take some solid zinc granules, just little chunks of gray zinc metal,
And you drop them into a glass test tube filled with dilute sulfuric acid.
and immediately the previously calm liquid starts furiously bubbling on the surface of the zinc.
What's actually happening in that test tube?
It's essentially a forced eviction. Sulfuric acid is a molecule made up of hydrogen, sulfur, and oxygen. The key ingredient is the hydrogen.
But the zinc metal is more chemically reactive than the hydrogen.
Yes, it has a stronger thermodynamic drive to bond with the sulfur and oxygen. So the zinc violently shoves the hydrogen atoms out of the acid molecule.
It just kicks them to the curb.
Pretty much. And it takes their place to form a completely new, stable compound called a salt. In this specific case, zinc sulfate.
Okay, let's unpack this. If the big bullying zinc atom just kicked the hydrogen atom out of its home, that hydrogen doesn't just cease to exist.
Right. Conservation of mass. It has to go somewhere.
So are we just left with a beaker full of loose, homeless hydrogen atoms floating around?
Not floating loosely for long. Individual hydrogen atoms are highly unstable and deeply unhappy on their own. They're desperate for stability.
So they pair up.
Exactly. Two hydrogen atoms snap together to form a molecule of H2, which is hydrogen gas.
And because hydrogen gas is incredibly light, it forms tiny bubbles on the surface of the zinc and just rapidly bubbles up out of the liquid.
And the cleverest part is how chemists actually prove that the invisible gas coming out of that test tube is hydrogen.
Oh, the pop test. You take a glass delivery tube, plug it into the bubbling test tube, and run the other end down into a bowl of ordinary soap solution.
So instead of the gas just escaping into the room, the soap solution starts blowing bubbles filled with this newly liberated hydrogen gas.
And hydrogen is the lightest element in the universe. So these soap bubbles detach and literally start floating upward toward the ceiling.
And then comes the diagnostic test.
You take a burning candle and you hold the flame near one of these floating soap bubbles. And the second the flame touches the bubble pop.
It makes a very sharp, distinct popping sound.
That little pop is actually a tiny controlled explosion, right?
It is. Hydrogen gas is insanely flammable. The moment it meets the heat of the candle, it rapidly combusts, reacting violently with oxygen in the air to form water vapor.
Releasing a burst of energy that creates that popping sound. It is such a dramatic sensory visual of an invisible process.
It really is one of the foundational demonstrations in chemistry. But what's fascinating here, and what often confuses students, is that it's not just acids that do this.
Right. This part of the research genuinely made me pause and scratch my head.
Because bases can also rip hydrogen out of its chemical housing.
Yeah. If you take those exact same zinc granules, but this time you drop them into a strong base like a solution of sodium hydroxide.
You have to put a Bunsen burner under it and warm it up a bit, but sure enough, it also produces hydrogen gas bubbles.
And you can trap those bubbles in soap and pop them with a candle just the same. But wait, if acids and bases are total chemical opposites, why do they both produce hydrogen when reacting with metals?
It's a great question. And furthermore, the notes explicitly state that bases are incredibly picky. This bubbling reaction doesn't happen with all metals.
Yeah, why are bases so picky while acids seem to attack everything?
This raises an important point about the structural nature of metals and bases. You see, acids are generally straightforward brawlers.
They'll fight anyone.
Basically. They're universally willing to hand over their hydrogen to almost any metal that is reasonably reactive. Iron, magnesium, zinc, whatever. It's a simple trade.
But bases are different.
Very different. Bases like sodium hydroxide don't have acidic hydrogen just waiting to be bumped off. For a base to react with a metal and produce hydrogen gas, it has to form a much more complex, bulky molecule.
Like what?
Well, when zinc reacts with sodium hydroxide, it forms a complex salt called sodium zincate. And forming this complex requires a metal that has a very specific, adaptable chemical personality.
And the research calls these amphoteric metals, right?
Yes, amphoteric, meaning they swing both ways,
Yeah.
essentially. Amphoteric metals can sometimes act a bit like metals and sometimes act a bit like nonmetals, depending on the environment.
So zinc can do this. Aluminum can do this.
Right. They are flexible enough to accommodate the complex structure the base demands. But most everyday metals, like a chunk of iron or a copper pipe, cannot.
They're strictly metallic.
Exactly. So if you drop iron into sodium hydroxide, it just sits there. The base looks at it, realizes it can't form the complex structure it wants, and just ignores it.
So acids are the aggressive brawlers that will throw a punch at almost any metal they see in the bar. But bases are highly specialized assassins that only engage with specific, flexible targets.
That is a highly cinematic way to describe it, but mechanically it holds up perfectly.
Okay, let's look at another major chemical clash. What happens when acids go up against carbonates?
Carbonates and hydrogen carbonates. These are incredibly common compounds. We're talking about baking soda, washing soda, the calcium carbonate in crushed eggshells.
Or even solid marble countertops.
Exactly.
So if you take sodium carbonate, which just looks like an unassuming white powder, put it in a test tube, and add some dilute hydrochloric acid to it, it doesn't just sit there.
No, it immediately starts fizzing and bubbling wildly, almost like a freshly poured soda.
But this fizzing is fundamentally different from the zinc reaction, isn't it?
It is. This is not highly flammable hydrogen gas this time. It is carbon dioxide gas.
The acid is relentlessly tearing apart the molecular structure of the carbonate. It forces the sodium to bond with the chlorine to make a salt. It makes a little water and releases all this trapped carbon dioxide gas.
And just like the popping bubble test for hydrogen, there is a specific diagnostic test for carbon dioxide.
The lime water test.
The lime water test. This is an incredibly elegant piece of chemistry. Lime water is an aqueous solution of calcium hydroxide.
And to the naked eye, it's perfectly clear, looks exactly like a glass of drinking water.
But when you take the invisible carbon dioxide gas bubbling off that reacting acid, and you pipe that gas through a tube down into the clear lime water,
The clear water turns milky white almost instantly. It looks like someone poured a splash of milk into the glass.
yes, and the mechanical reason for this is beautiful. The invisible carbon dioxide gas bubbles through the liquid and reacts directly with the dissolved calcium hydroxide,
And together, they form a new compound, calcium carbonate.
which is essentially microscopic chalk. And crucially, it is highly insoluble in water. It refuses to dissolve.
So suddenly, out of nowhere, millions of tiny solid white chalk particles materialize, suspended in the water.
Right. This dense cloud of solid microparticles blocks the light, turning the clear liquid into a cloudy, milky suspension.
But there's a twist to this experiment that legitimately sounds like a magic trick.
Ah, yes. Adding excess gas.
If you just keep pumping carbon dioxide into that milky, chalky water for a few more minutes, it goes completely clear again. I had to reread that part 3 times. Why does adding more of the invisible gas make the solid chalk disappear?
Because by adding excess gas, you force the chemical reaction to evolve into a second phase.
Okay, what does that mean?
Well, once all the calcium hydroxide is used up making the chalk, the continuous stream of carbon dioxide begins to react with the solid microscopic chalk itself.
The calcium carbonate.
Exactly. It forces a further structural change, transforming the calcium carbonate into a new compound called calcium hydrogen carbonate.
And here is the magic key. Unlike chalk, calcium hydrogen carbonate is highly soluble in water.
So the solid particles literally dissolve back into the liquid. As the new soluble compound forms, the milkiness fades away before your eyes, returning the liquid to crystal clarity.
It is stunning. Clear to milky, back to clear, entirely driven by invisible gases and solubility.
Which perfectly sets the stage for the ultimate chemical clash. We've seen how acids and bases terrorize metals and carbonates. But what happens when these two heavyweights are forced to fight each other directly?
Neutralization, the ultimate showdown.
Exactly. When you mix an acid with a base, they effectively destroy each other's defining properties. It's a chemical cancellation.
The acid neutralizes the base, and the base neutralizes the acid. Let's visualize this using our old friend, the phenolphthalein indicator.
The one that turns pink.
Right. You have a test tube filled with a strong base sodium hydroxide. You add a drop of the indicator so the liquid is glowing a bright, vibrant neon pink, highly alkaline.
Then you take a dropper full of hydrochloric acid and you start adding it to the pink base drop by drop.
And for a while, nothing seems to happen. It stays pink. But suddenly, at one specific critical drop, the entire tube flashes from neon pink to completely colorless water.
That exact microscopic moment is the point of neutralization. At that precise drop, the total number of acid molecules perfectly matches the total number of base molecules in the tube.
They have engaged in mutually assured destruction.
They have. And when the dust settles on that microscopic battlefield, what's left behind? A salt and water.
The base and the acid have violently torn each other apart, but their atoms haven't vanished. They just rearranged themselves.
The sodium from the base and the chlorine from the acid snap together to form sodium chloride, which is literally just ordinary edible table salt.
And the leftover hydrogen from the acid and the hydroxide from the base snap together to form H2O, plain water.
Two highly corrosive, incredibly dangerous liquids have violently combined to create a harmless beaker of slightly warm salt water.
It's wild to think about. You could theoretically drink the result of that reaction. I mean, please, to anyone listening, do not ever drink anything out of a chemistry lab beaker.
A very important disclaimer, but theoretically, yes. If the titration was down to the absolute molecule, you would just be drinking salty water.
Acid plus base yields salt plus water. That's the unbreakable rule. And understanding that rule actually helps us categorize the rest of the material world.
For instance, what happens if we react a metallic oxide with an acid?
Our research mentions an experiment with copper oxide. Copper oxide is just a dry black powder. It's a metal attached to oxygen.
And if you drop that black powder into a beaker of hydrochloric acid and stir it, the powder slowly dissolves and the entire liquid turns this beautiful, translucent blue-green color.
And that blue-green liquid is a solution of copper chloride, a salt.
Yeah.
And water is produced in the process.
So consider the logic. A metal oxide reacted with an acid to produce a salt and water. What else reacts with an acid to produce a salt and water?
A base. We just established that. So if the metal oxide is doing the exact same job as a base, it must be basic.
Precisely. We classify all metallic oxides as basic oxides. They are the chemical cousins of true bases.
Wait, let me see if I can reverse engineer this. If a metal oxide reacting with an acid acts just like a base, what about the carbon dioxide we were bubbling into the lime water earlier?
You're on?
Carbon isn't a metal, it's a non-metal oxide. And it reacted with the lime water, which is a base, to make the chalky salt.
So if a non-metal oxide reacts with a base to make salt and water, then non-metal oxides must be secretly acidic.
That is exactly right. You've hit on a fundamental symmetry in chemistry. Metallic oxides are basic, non-metallic oxides are acidic.
By observing these clashes, we uncover the underlying patterns of behavior that allow us to categorize the entire material world.
Okay, so we see all this bubbling, popping, neutralizing, and color changing. We see the macroscopic effects. But what is the hidden engine driving all this chaos?
Why does an acid act like an acid?
Right. Why is it so aggressive? To find the answer, we have to look closely at something that seems incredibly boring. Water.
Which brings us to a massive revelation, the absolute requirement of water for these chemicals to function.
This is where we transition from looking at colors and bubbles to the subatomic drivers. We have to look at ions.
The sources kick this off with a really clever logical trap. We know acids have hydrogen in them. Sulfuric acid has hydrogen. Hydrochloric acid has hydrogen.
So the totally logical common sense assumption is, if a chemical compound has hydrogen in it, it must be an acid, right?
It's a perfectly reasonable hypothesis, but it is fundamentally completely incorrect.
And to prove why it's wrong, chemists set up a very simple electrical circuit. You take a glass beaker, put a rubber cork at the bottom, and stick 2 iron nails into the cork so they are standing upright, not touching.
You connect wires from those nails to a battery, a switch, and a small light bulb.
Right now, the circuit is broken. Empty space between the nails. But if you pour a solution of dilute hydrochloric acid into the beaker, so it covers both nails, and you flip the switch,
the liquid completes the circuit. Electricity flows from one nail through the acidic liquid to the other nail, and the light bulb glows brightly.
This glowing bulb tells us something profound about the internal structure of the liquid.
For electricity to flow through a liquid, there must be a bridge. That bridge is made of ions, charged particles that can physically carry an electrical current across the gap.
The acid in the water has broken apart into positively charged hydrogen ions and negatively charged chloride ions, creating a superhighway for the electricity.
But here is the catch. If you empty the beaker, clean it, and this time you pour in a solution of glucose, which is just sugar water, or a solution of alcohol, and you flip the switch.
Absolutely nothing happens. The bulb stays completely dark.
Now, Glucose is C6H12O6. It has 12 hydrogen atoms. Alcohol is packed with hydrogen atoms, yet they don't conduct a single volt electricity.
What this beautifully simple experiment demonstrates is that merely possessing hydrogen atoms is not enough to make you an acid.
Exactly. An acid is a substance that is willing to release its hydrogen. It must decouple the hydrogen, leaving its electron behind, releasing it as a positively charged ion, an H+ ion.
And glucose and alcohol are highly stable. They keep their hydrogen atoms tightly bound up in their structure. They refuse to let them go.
Since they don't release any charged particles into the water, there is no bridge for the electrical current, and the bulb stays dark.
But the acids do let them go. They release the kraken, so to speak.
They do. But here is the crucial, mind-bending caveat. They only let them go if water is present to take them.
Here's where it gets really interesting. An acid isn't truly acting acidic without water. Our research details an experiment where you generate dry hydrogen chloride gas.
You take solid, dry table salt in a tube, add concentrated sulfuric acid, and it produces hydrogen chloride gas coming out of a delivery tube.
Now, if you hold a perfectly dry piece of blue litmus paper up to that jet of dry gas, absolutely nothing happens. The paper stays blue.
Which is astonishing if you think about it. Hydrogen chloride in a watery solution is hydrochloric acid, a notoriously aggressive, strong acid that will eat through metal.
But in its dry, gaseous state, floating in the air, it has zero acidic properties whatsoever. It cannot even change the color of a delicate indicator paper.
But the second you wet that litmus paper with a few drops from a sink, bringing just a tiny bit of liquid moisture to the party,
The gas touches the wet paper and instantly turns it blood red.
If we connect this to the bigger picture, it reveals a profound truth about chemistry. Properties are deeply relational. A molecule of hydrogen chloride is relatively stable on its own.
So water is the great enabler.
It is. When the hydrogen chloride molecule encounters water, the polar water molecules exert an incredibly strong electromagnetic pull on the hydrogen atom, literally tearing the acid molecule apart.
I love how the research explains what actually happens to that severed hydrogen ion. It notes that hydrogen ions cannot exist alone.
Right. Think about it. A hydrogen atom is just one proton and one electron. When the acid rips apart, the chlorine steals the electron.
So the hydrogen ion, the H+ amine, is literally just a bare, naked proton floating in space.
It is incredibly unstable. It cannot stand to be alone, so it immediately panics and latches on to the nearest water molecule.
It forcibly attaches itself to the H2O, changing that normal water molecule into H3O+, which chemists call a hydronium ion.
You will never, ever find a lonely H+ ion floating around by itself in an aqueous solution. It's a thermodynamic impossibility. You will only find these hydronium ions.
And that hydronium ion is the physical, microscopic embodiment of acidity, is the active agent. The more hydronium ions you have swarming in a glass, the stronger the acid.
And bases have their own mirror image version of this, right?
Exactly. When you dissolve a solid base in water, and by the way, bases that are soluble in water are called alkalis, the water pulls their crystalline structure apart to generate hydroxide ions, OH-.
So water tears acids apart to make H+, which becomes hydronium, and water tears alkalis apart to generate OH.
Which perfectly explains our epic neutralization reaction from earlier. When you mix a strong acid and a strong base, the aggressively needy H+ from the acid finds the negatively charged OH from the base.
They are magnetically drawn to each other, they snap together, and what is H plus OH?
It's H2O. It's just water. The dangerous, highly charged ions literally cancel each other out to form completely harmless water molecules.
It is the ultimate, elegant chemical balancing act. But while the resultant water is harmless, we must address the physical, terrifying reality of initiating this process.
Yes, the safety rules. The danger of dilution.
If you go into a lab, you will see very stern warning signs on bottles of concentrated acids. Dissolving a strong acid or a strong base in water is a highly exothermic process.
Exothermic, meaning it generates and releases a massive amount of heat into the environment.
Tremendous heat. Heat enough to boil water instantly, which is why there is an absolute non-negotiable golden rule in every chemistry lab on Earth.
If you are diluting an acid, you must always add the acid to the water slowly, drop by drop, while stirring constantly. You must never, under any circumstances, add water to a concentrated acid.
Okay, let's think about this logically. Why does the order matter so much? It's exactly the same two liquids ending up in the exact same beaker.
Why is one way safe operating procedure, and the other way a recipe for a catastrophic emergency room visit?
It all comes down to the physics of heat capacity and volume. Water has an exceptionally high specific heat capacity. It can absorb a massive amount of thermal energy before its temperature actually rises significantly.
So if you have a large beaker filled with water and you add a few tiny drops of concentrated acid, the reaction immediately releases a spike of heat.
But that heat is instantly swallowed up and dispersed safely by the vast ocean of water surrounding it. The water acts as a massive thermal shock absorber.
Okay, that makes sense. The water takes the hit.
Exactly. But let's reverse the scenario. You have a beaker full of highly concentrated, syrupy sulfuric acid. There's almost no water in there.
Now, you take a dropper and let a single drop of liquid water fall into that concentrated acid.
Oh, no. Because now the water is the minority.
Precisely. The moment that single drop of water hits the surface of the acid, the hydration reaction happens instantly. A massive amount of heat is generated right at the surface.
But there is no ocean of water to absorb it. The acid itself doesn't have the heat capacity to safely dissipate that energy.
So all that intense heat just dumps straight back into that single tiny drop of water. And what happens when a drop of water absorbs a massive amount of heat in a microsecond?
It flashes into steam. It boils instantly.
It expands to over 1,000 times its liquid volume almost instantly. This micro-explosion of steam violently propels the surrounding concentrated acid outward in every direction.
It will spray out of the beaker onto the benchtop, onto your clothes, and potentially into your eyes, causing severe chemical burns.
The sudden, localized extreme thermal shock can even cause the glass beaker itself to shatter into shrapnel.
That is terrifying. The mental image of a steam explosion firing battery acid into the air. Okay? Add acid to water slowly while stirring. Got it? I will never forget that.
Now, our sources note that when we successfully and safely mix water with an acid or base, we are decreasing the concentration of those ions per unit volume.
But you're spreading them out. The space gets less crowded with dangerous ions. That process is called dilution.
You are watering down the army. But since we just learned that water determines if a substance acts like an acid or a base, how do we measure exactly how much power those diluted ions have?
How do we know if we're dealing with a mild, pleasant tang in our salad dressing or a corrosive existential threat to our skin?
And that leads us to the universal measuring stick, the pH scale, and how it governs biological warfare.
The pH scale is one of the most elegant, universally applied measuring tools in all of science. It simply assigns a number to that ion concentration.
To measure it visually, chemists use a universal indicator. It's a carefully crafted mixture of several different indicators that smoothly change through an entire spectrum of colors, like a rainbow.
And the numerical scale itself ranges from 0 to 14, with the dead center, exactly 7, being perfectly neutral. Pure distilled water is a 7.
And I love this little historical detail hidden in our research. The P in pH isn't just a random letter. It stands for potens, which is a German word that translates to power.
So pH literally translates to the power of hydrogen.
Exactly. A value less than 7 indicates an acidic solution. And the closer it gets to 0, the more incredibly dense the hydronium ions are packed in.
Meaning the stronger and more dangerous the acid. A pH of 2 is vastly stronger than a pH of 5.
And as you move past 7, climbing up towards 14, the hydrogen ion concentration drops off a cliff, and the hydroxide ion concentration takes over,
Making the liquid increasingly basic or alkaline. A pH of 13 is a highly corrosive, dangerous base, like drain cleaner.
Now, what's absolutely crucial to understand is that this pH scale isn't just arbitrary laboratory math. This scale physically dictates the boundaries of life and death on Earth.
Yes, the sources bring this reality right back to our own biology. The human body operates in an incredibly tight, terrifyingly narrow pH band, specifically between 7.0 and 7.8.
We are slightly, delicately alkaline creatures. If the pH of your bloodstream drops below 7.0 or rises above 7.8, your cellular machinery literally begins to break down.
Proteins begin to unravel and denature. Enzymes stop functioning. Your organs fail. Life simply ceases.
All of evolutionary biology relies entirely on complex buffer systems maintaining tight pH balances.
Yeah.
And it's not just human blood. The delicate balance extends to the environment.
Acid rain is a great example. Normal rain is naturally a little bit acidic, with a pH around 5.6, because it absorbs natural carbon dioxide from the air.
But when heavy industrial pollution pumps sulfur dioxide and nitrogen oxides into the air, the rain absorbs them, and the pH plummets below 5.6.
It becomes highly corrosive acid rain. When that acidic water flows into rivers and lakes, it lowers the pH of the entire body of water.
Fish, insects, and aquatic plants simply cannot survive in that altered chemical environment. Their biological processes shut down.
And speaking of toxic, acidic environments, our research casually drops an absolutely incredible fact about the atmosphere of our planetary neighbor, Venus.
Oh, yeah. You look up at the night sky, you see this beautiful, bright, glowing orb that we call the evening star. It looks so peaceful.
But if you were actually falling through the atmosphere of Venus, those thick white and yellowish clouds aren't fluffy water vapor like on Earth.
No, they are dense, opaque clouds of pure, concentrated sulfuric acid.
Venus is the ultimate cosmic cautionary tale of runaway atmospheric chemistry. The text asks a rhetorical question: do you think life can exist on this planet?
Given what we just discussed about the incredibly narrow, fragile pH tolerance of life, an atmosphere that literally rains sulfuric acid makes Venus a chemical hellscape.
Any life form as we know it would be instantly dissolved. But back down here on Earth, we actually utilize extreme pH inside our own bodies as a tool.
Our stomach actively produces hydrochloric acid, the exact same corrosive stuff that makes solid zinc violently bubble and pop.
It is essential for our survival. That highly acidic environment with the pH down around 1.5 to 3.5 physically breaks down complex food molecules.
It acts as a security checkpoint, killing off harmful bacteria and pathogens we inevitably swallow with our food.
But we all know what happens when we eat too much spicy food or we're super stressed and the stomach produces too much of this acid.
Indigestion, heartburn, a literal physical burning pain in your chest. And how do we treat it? We take antacids.
Antacids are exactly what they sound like, antacids. They are mild, ingestible bases. A classic example is milk of magnesia, which is magnesium hydroxide.
You swallow the chalky basic liquid, it travels down your throat, meets the pool of excess acid, and just like the phenolphthalein drop experiment, they clash.
They neutralize each other, leaving behind completely harmless magnesium chloride salt and plain water. The acid is destroyed, and your burning stomachache disappears.
It's industrial chemistry solving a biological crisis in real time inside your torso. Another fascinating biological interaction governed by pH concerns our teeth.
Tooth decay. This was a revelation to me. The enamel covering our teeth is made of calcium hydroxyapatite.
It is the single hardest, most durable substance in the entire human body. It is essentially biological armor.
And yet, this impenetrable biological armor has a fatal chemical flaw. If the pH inside your mouth drops below exactly 5.5, the environment becomes acidic enough that this indestructible armor actually begins to corrode and dissolve.
And what causes the pH in your mouth to drop? Microscopic bacteria living on your teeth, degrading leftover sugar. As they eat the sugar, they excrete acid as a metabolic byproduct.
Basically, bacterial waste. I read this and had to ask, if tooth enamel is the hardest substance, isn't it an evolutionary design flaw that microscopic bacteria can degrade it so easily?
It absolutely seems like a gaping vulnerability in our design. But from an evolutionary standpoint, early hominids weren't eating highly processed, sticky sugars that fuel massive acid spikes.
Our modern diet has weaponized our own naturally occurring oral bacteria against our enamel. But once again, we use chemistry to fight back.
Toothpaste. If you test most toothpastes, you will find they are generally basic or alkaline.
Chemically, the basic toothpaste is actively neutralizing the excess acid the bacteria have already produced, forcibly raising the pH of your mouth back into a safe neutral zone above 5.5.
Instantly halting the corrosion of your enamel. Have you ever wondered why your mouth feels kind of fuzzy or sour after eating a ton of candy? That's the pH drop happening in real time.
It's amazing how much of our mundane daily grooming routine is just basic chemical management. And it turns out humans aren't the only ones playing this game.
Plants and insects have been waging chemical warfare using pH for millions of years. Have you ever been stung by a honeybee? It is a sudden, sharp, lingering, burning pain.
And the reason it burns so badly isn't just the puncture wound, it's because the bee's stinger has literally injected an acidic liquid directly under your skin.
And what is the highly effective traditional cure? Applying a mild base, like a thick paste made of baking soda and water, directly to the sting area.
The alkaline baking soda seeps in, neutralizes the injected acid, and the burning pain subsides almost magically.
But the most amazing, almost poetic example of ecological chemistry in our research is the nettle plant. The stinging nettle is a wild plant covered in tiny, microscopic stinging hairs.
If you accidentally brush against a leaf, those hairs snap off and act like tiny hypodermic needles, injecting methanoic acid directly into your skin,
causing a terrible, blistering, burning rash. But nature often provides an antidote in close proximity. the dock plant.
A centuries-old traditional remedy is to look around the immediate area to find a dock plant, which incredibly almost always grows right next to the stinging nettle.
You take a leaf, crush it up, and rub the juices vigorously on the burning sting. And obviously, based on the laws of neutralization, the dock plant must contain a natural base.
It instantly neutralizes the methanoic acid from the nettle. It is a remarkable ecological pairing, the acidic poison and the alkaline cure growing side by side in the dirt.
Our sources even provide a whole table of natural acids we encounter every day. The tangy vinegar on your fries, acetic acid. Oranges and lemons get their punch from citric acid.
Tamarind uses tartaric acid. Tomatoes, surprisingly, have oxalic acid. Sour milk gets its flavor from lactic acid.
Which highlights a vital point to remember. Acids and bases are not just bubbling, neon-colored industrial chemicals sitting in vats. They're the fundamental building blocks of flavors and natural ecological processes everywhere.
Okay, so we've explored the aggressive acids, we've analyzed the bases, we've seen how they clash, but when these chemical wars finally conclude, what exactly is left behind on the battlefield?
We know it's salt and water, but what is a salt, really? The answer brings us to the salt family tree and a massive piece of industrial wizardry called the chlor-alkali process.
When the average person hears the word salt, they almost exclusively think of table salt. But in chemistry, salt is a massive, incredibly diverse category of compounds.
By definition, any ionic compound formed by the neutralization reaction of an acid and a base is a salt. And the research explains that salts belong to vast families based on the chemical radicals they share.
For example, sodium chloride and sodium sulfate both belong to the family of sodium salts because they share that positive sodium ion from their parent base.
But sodium chloride and potassium chloride belong to the family of chloride salts because they share the negative chloride ion from their parent acid.
It's like tracking a chemical genealogy. Furthermore, not all salts are perfectly neutral with a pH of 7. The resulting pH depends entirely on the relative strength of their specific parents.
If a brutally strong acid and a fiercely strong base have a baby, they completely cancel each other out, and the resulting salt is perfectly neutral, like sodium chloride.
But if a strong, aggressive acid neutralizes a weak base, the acid dominates the genetics. The resulting salt will be an acidic salt, possessing a pH below 7.
And vice versa. A strong, powerful base and a weak acid produce a basic salt, with a pH hovering above 7.
But for the sake of human history, let us return to the most famous member of this family, sodium chloride, table salt.
Have you ever wondered where all the salt in the world comes from? Seawater contains massive amounts of dissolved salts. Over millions of years, ancient seas became landlocked and dried up, leaving behind enormous beds of solid rock salt buried deep underground.
And unlike the pure white salt on your table, rock salt in the earth is usually brown because it's full of earthly dirt and impurities.
And this seemingly simple, brown, dirty mineral has literally shaped human history. Our sources bring up a historical example here. Mahatma Gandhi's Dandi March in 1930.
A massively pivotal moment in India's struggle for independence. The British colonial government had enacted a strict monopoly on salt production and imposed heavy taxes on it.
Gandhi's decision to march 240 miles to the coastal village of Dandi to boil seawater and make his own salt was a brilliant act of nonviolent civil disobedience.
Right, because sodium chloride is a fundamental biological necessity for every human being on Earth to survive. By defying the empire and claiming the right to freely harvest it from the ocean, he was claiming a fundamental human right to life.
It's powerful to think that a simple chemical compound could be the focal point of an entire revolution. But the importance of sodium chloride doesn't stop at historical protests.
No, this common salt is actually the ultimate raw material for a massive chunk of our modern industrial world. This is where we encounter the chlor-alkali process.
It is an absolute masterpiece of industrial-scale chemistry. So imagine a massive chemical plant. You take a highly concentrated aqueous solution of sodium chloride, which is just incredibly strong salt water, called brine.
You pump this brine into a massive tank, and then you run a massive direct electrical current straight through the salt water.
What you are doing here is called electrolysis. The strong electrical current forces the atoms to detach and recombine in new, highly valuable configurations.
When you zap it, the brine decomposes into 3 distinct products. At the positive pole, negatively charged chloride ions bubble up as highly toxic greenish-yellow chlorine gas.
At the negative pole, water molecules are split, releasing hydrogen gas. And what is left behind in the liquid is a highly concentrated, incredibly alkaline solution of sodium hydroxide.
Hence the brilliantly literal name, The chlor-alkali process. Chlor for the chlorine gas bubbling off, and alkali for the basic sodium hydroxide left in the vat.
Every single one of those three products is incredibly useful. The hydrogen gas for clean fuels, the chlorine gas for water treatment and plastics, the sodium hydroxide base for making soaps and paper.
But the true ingenuity of the chemical industry lies in how we take these secondary products and aggressively combine them further to make even more essential household items.
Let's talk about bleaching powder. You take that toxic, deadly green chlorine gas you just harvested from the saltwater brine, and you pass it over dry, solid slaked lime,
which is calcium hydroxide. The resulting chemical reaction produces a new complex compound, calcium oxychloride.
But to consumers, we just call it bleaching powder. It's used on a massive scale for bleaching cotton and textile factories, bleaching wood pulp in paper factories, and for disinfecting public drinking water supplies.
Bleaching powder is essentially a clever way to trap the disinfecting power of chlorine gas into a stable, solid white powder that you can safely transport in a cardboard box.
Then, moving from the laundry room to the kitchen pantry, we have baking soda, chemically known as sodium hydrogen carbonate.
We use baking soda in the kitchen all the time. But look at how it's made. It is produced on an industrial scale by reacting cold, concentrated sodium chloride brine with water, carbon dioxide, and ammonia.
The result is a mild, non-corrosive basic salt. And it is so incredibly versatile. Because it is a mild base, you can literally eat a pinch of baking soda dissolved in water to neutralize heartburn.
It acts as an antacid, but its primary magical use is in baking.
When bakers use baking powder, which is a mixture of baking soda and a weak edible acid like tartaric acid, nothing happens while it's dry.
But when you mix it with water to form a wet dough and then place that dough in a hot oven, a neutralization reaction kicks off right there inside your cake pan.
The heat speeds up the reaction between the basic soda and the acidic tartaric acid. And just like we learned earlier, what happens when any carbonate reacts with an acid? It violently releases carbon dioxide gas.
Those thousands upon thousands of tiny carbon dioxide bubbles are instantly generated, but they get trapped in the sticky, dense web of the gluten in the dough.
As the gas expands, the bubbles push outward, forcing the heavy dough to stretch and rise upward, giving the finished bread or cake that light, fluffy, porous texture we love.
And the reason bakers include that specific tartaric acid is crucial. If you just used plain baking soda, it would leave behind sodium carbonate in the cake, which is a strong base.
And bases taste bitter? Your beautiful birthday cake would taste like a bar of soap. The tartaric acid neutralizes that bitter base as the cake bakes.
The text also notes a much more dramatic use for baking soda outside of the kitchen. Soda acid fire extinguishers.
Inside some of them, you have a large reservoir filled with a liquid solution of baking soda. Suspended inside is a tiny, fragile glass vial filled with highly concentrated sulfuric acid.
When you pull the pin and bang the extinguisher knob, it shatters the glass vial. The strong acid instantly mixes with the massive amount of baking soda base.
And an immense, overwhelming volume of carbon dioxide gas is violently produced in a fraction of a second. That pressurized gas forces the liquid out of the nozzle at high velocity.
And because carbon dioxide is heavier than oxygen, it blankets the burning object, suffocating the fire by cutting off its oxygen supply.
So what does this all mean? The exact same simple brown rock salt buried in the earth is literally the secret chemical grandparent of both the stuff that violently suffocates raging fires and the stuff that makes our birthday cakes light and fluffy.
The versatility of these raw materials is astounding. And there is one more major derivative we must discuss, washing soda.
Chemically known as sodium carbonate. If you take sodium carbonate and recrystallize it by dissolving it in water and letting it form solid crystals again, you get washing soda.
It's an aggressive cleaning agent, but there is a very specific, very curious detail in its chemical formula that our research highlights.
The exact chemical formula is written as Na2CO3.10H2O. That .10H2O means that exactly 10 water molecules are chemically attached to every single sodium carbonate molecule.
Which raises an immediate, glaring physical paradox.
Exactly. If you buy washing soda at the store, it is a dry, white powder. You can hold it in your bare hand and your hand will not get wet. But the formula literally says it is packed full of water.
Does that 10H2O signify that the washing soda is secretly wet? This apparent contradiction leads us perfectly into our final concept, the illusion of dryness, or the concept of water of crystallization.
The research asks us to look at copper sulfate crystals. If you've ever seen them in a lab, they are these beautiful, vibrant, translucent blue crystals. They look like jagged pieces of shattered blue glass.
If you pick one up, it feels completely dry and hard. but their true chemical formula is QSO4.5H2O. Every repeating unit of that lattice has exactly 5 molecules of water secretly locked away inside it.
And the experiment to prove this water exists is so elegant. You drop a few of these dry blue crystals into a dry glass boiling tube, and you hold the bottom over a hot Bunsen burner flame.
As the crystal heats up, 2 incredible things happen. First, the upper part of the glass tube starts to fog up. Tiny, visible droplets of liquid water condense on the inside of the glass.
Physical water that was just violently driven out of this supposedly completely dry crystal by the intense heat. And the second thing, you look down at the crystal itself and it has completely changed color and texture.
It loses that vibrant blue color entirely, and it crumbles into a chalky, pale, dead-looking white powder. The heat has forcefully evaporated the water of crystallization entirely out of the solid atomic structure.
Here is an analogy for you. Think of the solid crystal not as a brick wall, but as a complex skyscraper. The copper and sulfate atoms are the steel girders, but the water molecules are acting as invisible molecular scaffolding, holding the architecture in its correct shape.
The water is a structural building block. When you apply intense thermal energy, you burn away the water scaffolding. Without it, the precise molecular architecture collapses and the building crumbles into white dust.
The water is chemically bound into the crystal lattice at fixed points. It is absolutely not wet in the macroscopic liquid sense that we understand.
And you can instantly prove that it's specifically the missing water that caused the collapse. If you take that white dehydrated powder, let it cool down, and then you add just 2 or 3 tiny drops of liquid tap water back onto it.
The reaction reverses instantly. The white powder aggressively absorbs the water, the structural scaffolding rebuilds itself in milliseconds, and the vibrant blue color magically reappears as the crystal lattice heals itself.
It is stunning to watch, and this highly specific chemical quirk is the entire basis for setting broken bones in emergency medicine. Plaster of Paris.
Our sources explain that in nature, there is a common salt called gypsum. It's a hard, solid rock. In manufacturing, if you heat raw gypsum in a kiln to exactly 100 degrees Celsius, the boiling point of water, it begins to dehydrate.
But it specifically loses 1.5 molecules of water, leaving behind calcium sulfate hemihydrate, meaning it only has half a molecule of water attached to it.
Which sounded impossible to me at first. You can't chop a water molecule in half. But the chemistry notes clarify that it just means 2 separate molecules of calcium sulfate are sharing a single, whole molecule of water between them.
Like 2 people huddled closely together sharing one umbrella. This specific partially dehydrated white powder is what we call plaster of Paris.
You buy it in heavy paper bags. It's a fine, dry, dusty white powder. But the moment an orthopedic doctor mixes it in a bowl with a little bit of liquid water to make a thick paste and wraps it around your broken arm,
the chemical reaction runs rapidly in reverse. The hemihydrate is starved for its missing water. It eagerly absorbs the liquid water you just added, chemically integrating it back into its structure.
The scaffolding snaps back into place. Over the course of about 10 to 15 minutes, that wet paste violently crystallizes back into solid, rock-hard gypsum. It generates noticeable heat on your skin, and it locks your fractured bone perfectly in place so it can heal.
From a dry powder to a wet paste, back to a solid rock, entirely governed by the precise invisible movement of microscopic water molecules sliding in and out of a crystalline lattice structure.
It just blows my mind when you stop to think about the mechanics of it. The level of hidden complexity in the most mundane objects is staggering.
Indeed. We've journeyed through quite a landscape today.
We really have. We started this deep dive looking at color-changing cabbage juice and ruined curry stains, learning how nature chemically alerts us to invisible environments.
We watched an aggressive zinc atom tear acids apart to blow explosive hydrogen bubbles, and we broke down why adding a drop of water to a concentrated acid can cause a violent steam explosion.
We examined the delicate tightrope of the pH scale, exploring how our own bodies use corrosive acids to digest food while relying on alkaline toothpaste to protect our enamel.
We traced the majestic lineage of a simple pinch of table salt, from ancient oceans to Gandhi's revolutionary march to the massive industrial plants that ripped the salt apart with electricity.
And finally, we uncovered the illusion of dryness, realizing that the solid plaster in our walls and the medical casts on our bones are secretly held together by locked, invisible structural water.
It really changes how you look at the physical world, doesn't it?
You can't just look at a kitchen counter or a glass of water and see stillness anymore. You know the war that's happening just beneath the surface. But as we wrap up, I want to leave you, our listener, with a final thought to mull over based on everything we've unpacked today.
Consider this. We learned that dry hydrogen chloride gas is completely powerless without a single drop of moisture to activate its acidic nature. And we learned that dry copper sulfate crystals are secretly hiding actual water trapped inside their solid architecture.
So as you go about your day-to-day, look around you at the objects you take for granted and ask yourself what other supposedly neutral, safe, or dry objects resting in your daily life are actually just locked in a frozen chemical stalemate.
What is sitting on your desk or in your pantry right now just waiting for a single tiny catalyst, a drop of water, a spark of heat, a slight shift in pH to suddenly reactivate its chaotic, highly reactive origins?
The slightly terrifying but mostly beautiful thought. The entire physical world around us is just a bunch of paused chemical reactions waiting for someone to hit play. Thank you so much for joining us on this deep dive. Keep questioning the invisible mechanics of the world around you. Keep looking for those aha moments, and we will see you next time.